do in the GDC lecture. So I want to explain a certain new kind of line to you, though. So I say that the dual quaternions, they can represent a line anywhere. And there's a certain special kind of line that's a bit hard to get your head around, but it's very, very useful, it turns out. So this is the horizon line, which is a line that you've looked at all your life. It is a proper line, and the dual quaternions can represent this line. You might be compelled to say that, oh, the horizon line is more like a circle, but no, if you look at it wherever you go, it's always a line. It's always a straight line from your point of view. Another example of a line like this is sort of the Milky Way in this rather beautiful picture. The Milky Way is in some sense extremely far away, right? We're talking about a line here that's so far away that when you look at it and you move yourself around, it doesn't appear to change its position from your point of view. All right, and let me try to give a reason why we might want to care about quaternions as opposed to using vectors for everything. Here I've got a random pattern of dots. I promise that they're random. People sometimes get suspicious. They really are random. Here we've got the same random pattern of dots, and I'm going to lay them on top of each other very, very carefully. All right. And you're going to see, when I do this, once again, the same random pattern of dots. Very, very, very boring. But now I'm going to move it, all right? I'm going to perturb it slightly. So we get, did I move it in a special place? No, let me move it again. Oh. It's always circles. You're seeing circles that are going around some point that we've got here. That's because when I perturb this thing, I'm doing a Euclidean transformation. I'm not squashing or stretching or morphing it in any way. I'm doing a Euclidean transformation. And we're talking about 2D here. A 2D Euclidean transformation is always something that preserves a certain point, right? There's an optical illusion going on. Like if I make it go really far, it sort of disappears. Like here, right now, the circles are getting smaller and smaller, and they're getting bigger and bigger. But here I can make them small, and then it disappears. It's still a rotation around this point here. But yes, it's just a way for your eyes to see it. But there's a funny trick that you can do with this, all right? So I'm going to start out with the center of rotation here, and I'm going to do a move that's going to cause it to end up over here, all right? I'm going to kind of rock it from side to side. I want you to and we're going to think about what happens in between, all right? So here we go. So the circles are somehow going off on one side, and they're coming back on the other side. We seeing? Oh, let's see. Bit easier if I can see it. All right. All right. Whoop. They go off on one side, and they come back on the other side. Two things to say about this. Number one, okay, we're starting out like this. It goes on like that. Then it comes back on the other side. But there's an intermediate stage here where suddenly it's stopped being a rotation and it's briefly become a translation, right? It's kind of like the circles here that you see have become straight lines. And that's kind of like saying that the circles have become infinitely big, right? Joan's going to be talking about this kind of thing later a lot. Yeah, and that's a strange thing to say, but it's true. A translation, which is a mathematician's way of saying a movement, a translation is a rotation around a point that's very, very far away. Okay. Another thing to say about this, like, wouldn't it be a shame if someone were to say, do you know what, all rotations are rotations around the origin? If you want to rotate around somewhere, you should translate to this wonderful place called the origin. You should rotate there, and then you should translate back. Terrible idea. It's really denying yourself some very beautiful mathematics. We don't want to do that. We don't want to be scrubs. All right. Another way of illustrating the same thing. Let me see how much time I've got. Yeah, it's okay. So here I've got a Lego motorbike, right? let me show, and I've attached some poles to its axles. Here's a fun thing you can do. If I put this Lego motorbike down like this, with the handlebars turned very far, it turns out that if I push the motorbike back and forth, it is performing a rotation around a point here. It's performing a rotation, well, take it from me. It's performing a rotation around the place where its two axle lines cross each other. If I turn the handlebars a bit less, it should still perform a rotation around this place where I've got my finger. So it's like if you were going around a roundabout or a traffic circle, as they say in the US, the center of the traffic circle would be here, that you're going around with your handlebars turned like this. Let's ask the dangerous question that now, though. What if the handlebars are completely like this? What if it's parallel? Well, obviously you know what the motorbike does. The motorbike will just go back and forth. It's not doing a rotation, it's doing a translation. What's happened to the place where the axles crossed? Well, it's gone very, very far away, and you can kind of see where it goes, all right? If I bring that close, I've got a picture illustrating this just in case, but yeah, you can. I'm holding them parallel, but you can kind of see that somewhere back there, right, the lines are meeting each other. All right. So here we've got them meeting at this point over here, and this motorbike performs a rotation around this line. Here, if you extend these lines, they meet at a point on the horizon, and the motorbike, when it goes forward, it's doing not a rotation, and certainly not around a line, because it can't go all the way around that line, but it's doing a transformation that preserves that line. Another way of looking at the same thing, here we've got a carousel, and I want you to look at the poles in this carousel. They're all clearly going around this central spindle of the carousel. Over here, you've got a bunch of trees that are behaving quite a lot like the poles, and they're sort of, in a sense, going around the sun, right? Okay. To overlay those, here we've got the motorbike going around the carousel. Here we've got the motorbike going around the sun, in some sense. And one last thing here. So one reason that people in the games industry care about a lot about dual quaternions is that they solve this bug, which is called the candy wrapper effect, because it's kind of like this woman's skin is like a balloon or something like that. This woman was animated using 4x4 matrices, which is a terrible thing to use for animation. This woman's arm was animated using dual quaternions, nice dual quaternions, and Blender, Houdini, 3D Studio Max, and Maya all give you the option nowadays to use dual quaternions if you want to. In order to apply them, you have to use something called the exponential and logarithm functions, and at Imagination Technologies, our GPUs are way better than anybody else's GPUs, because we can do this thing called sync, which feeds into exponential and logarithm and speeds them up a little bit. Yes, so Imagination GPUs, they're just the best. All right, so part 2, making things from reflections. Okay, good. I'm not doing too badly for time. So, we want to think about reflections a lot. Projective geometric algebra, or specifically Euclidean plane-based geometric algebra, is a wonderful way of thinking about reflections and solving lots of problems in video games. And reflections tend to start with planes, and one kind of video game where you care a lot about planes is a snowboarding video game, right? If you were programming a video game about snowboarding, you would care a hell of a lot about where is the plane defined by the board and where is the plane defined by the snow, especially if you're about to land on the snow, right? You might want to care about, where do I put the marking on the snow where the player landed? How do I check whether the player should tumble over, this kind of thing? You care a lot about those planes, and that's got to motivate us, because we're going to think about planes a lot, right? So here's how we represent a plane in most game engines. I think all game engines, right? So we've got an x part, a y part, a z part, and a d part. The d part is in some sense displacement from the origin, but we're going to leave it as 0 for now. We've actually got an interesting way of thinking about displacement from the origin. But yes, this plane, we can say that this is like its normal vector. That's what they tend to say. The x part, the y part, and the z part is the normal vector of the plane, and you can indeed visualize it this way. How about this plane? Well, this plane has got the normal vector, but the normal vector is extended. And actually it's describing the same plane. This plane has got the same normal, it's not got the same normal vector as this plane, but it's facing in the same direction as this plane. So this does, multiplying this by 2 does nothing, which should remind you a lot of quaternions, right? This is what we mean by homogeneous representation. Okay, so you can kind of forget about the normal vectors. You kind of want to think of these as just being the plane, in the same way that you think about x, y, z, w as being just the quaternion. All right. Here we've got our basis planes, x plane, y plane, z plane. This is the plane whose normal is in the x direction. Points on it have x equal to 0, which is a bit confusing, I know. Terribly sorry about that, but it's the way it is. Points on this plane have x is equal to 0, and the plane is described by x is equal to 1. Yeah, sorry, you just got to get used to it. This plane is the plane whose normal is in the y direction. Points on it have y is equal to 0. Here's the z plane, and points on it have z is equal to 0. These also get called E1, E2, and E3 in geometric algebra. In fact, by everybody else that you'll hear from this week. But yeah, but I'm video games, so X, Y, Z. All right, there's another kind of plane that we want to think about, though, which is this plane. All right, what's this? We've got x, y, z is equal to 0, so this is somehow a plane that isn't facing in any direction? That's a bit weird. But right, but it's d is equal to 1, so it's somehow displaced from the origin? Ugh, what's that plane? Well, the answer is that that plane, if you're a video game developer at least, it's essentially your skybox, all right? Or rather, it is the sky. That's a bit of a simplification, temporary simplification, but this does pretty well. And you might notice that this thing isn't a plane. Right, it's a sphere. It's not a plane. But in this context, we're talking about a sphere that's so big, right? It's so big that it's behaving like a plane, all right? What is the sky? The sky is kind of like a big sphere that surrounds you, but it's a sphere that's so big that if you went up to it and measured how curved it is, you'd find that it isn't curved at all right? It's a sphere that's become like or like a circle that's become like a line, like in the thing that I showed you earlier.